Okay, are we up? All right, guys. We are slightly behind, like 10 minutes behind. So I'm probably not going to be able to finish today's lecture simply because I timed it to 80 minutes. But let's start again. So here's where we were in the last class. We saw how we trained a network. The network had some target function of this kind that you actually wanted to learn, and your current network is going to be your current network is some other function, which is f of x w. W are the parameters, and you train it using a bunch of training samples where for each sample you know the x value and you know the desired output at the target function. And so you would have a bunch of these samples, and you can actually measure how much they are off by in each case. And this, the sum of these lengths, where these lengths are quantified using a divergence function, or the average of these lengths gives you some idea of how far the current function is from the function that you actually want to estimate. And what were the properties of the divergence function that we wanted? Zoe, do you remember? And what is the third one? Anybody remember? You there? You with the really small characters. What's that? The lady in the middle. Yes, and you there. It should be 0 when these two are equal. It should always be non-negative. And differentiable is something that we wanted. So once you write it this way, since all of these guys are known, x is given. This is a training sample, right? So what is the only thing that you can modify when you compute the average of the distances over a bunch of training samples? What is the only thing left over here? There are different ways of changing. You could try to change this shape or this average error by either moving x or by changing the function itself, right? And changing the function itself is the same as changing the weights, the parameters. So the loss, once x is given to you, is a function of only the parameters, and this is what we're going to try to minimize with respect to the parameters, right? So this is where we were. And this is a function, this is an instance of function optimization. You have a function of some terms, you want to optimize it, so you're going to spend some of the class on the concept of function optimization. Now, Prithvi, what do you understand by derivative?
The derivative gives you, I guess, small increment or increments in function with respect to increment.
So if you have any function, the derivative tells you, if I have some function, and if I look at the value of the function at any x, then and if I make a small increment of delta x at this point, the function value changes. And so this difference, delta y, is a function of delta x, right? And the derivative is defined as the multiplicative factor alpha. It depends on where x is, that you multiply delta x by to get the corresponding delta y for small enough delta x. This is the only way of defining the derivative. There's no other way of defining the derivative which is correct, okay? So we often write this as dy over dx, right? Why is this wrong? Ryan, why would it be wrong?
It doesn't include the alpha.
That is the alpha, right? Representing alpha is dy over dx, right? I have to look at this. Can you make that bigger? So Cecilia, why is that wrong? Saida.
I think because it implies that it tells us how much, like, the derivative of the function is, 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 like, the deriva the like the number that.
Okay, all of you are kind of struggling. Can I write this? Yes, Owen.
That is a ratio,
Yeah.
and the derivative is not the ratio, right?
The derivative can be thought of as a ratio, but can I write 1 over x when x is a vector?
No.
Can I write 1 over x when x is a matrix? This notation is not generally correct, yes? So that's why this notation is kind of bad in the general case. But then, so this term is what I want burned in your heads, because we're going to keep seeing it again and again, all right? Now, when you have a scalar function of a scalar variable, so the output is a scalar, the input is a scalar. In that case, delta x is going to be a scalar, delta y is also going to be a scalar, right? It tells you how much a small change in x is going to change y. And in this case, you can indeed write dy over dx, but it's still not a very nice notation, right? If I write y equals f of x, there are two different ways of indicating this. I can write dy over dx or f prime of x. Which of these two seems more reasonable to you, Lewis? Liwei, you. So which of these two would be same?
The second one,
Why?
because the reason you just mentioned is that what if x, y are matrix or vector?
No, but I'm speaking of a scalar function of a scalar variable. Yukun, why would the second one be more reasonable?
I don't like to write quotient.
Pardon me?
I don't like to write the quotient.
You don't like it, you don't like it. Okay, Wang, tell me why he's wrong to not like the second form. Does this indicate that this is actually a function of x? No, right? The derivative depends on where x is. So this guy, the derivative here, is going to be very different than the derivative here. This notation actually is a much cleaner notation. It tells you where you are, right? That the slope depends on where you are, right? Okay. Now, when I'm speaking of a scalar function of a scalar argument still, right? Now, the derivative is given by this guy. If I have a function of this kind, which is going up, then every time I have a small increase in dx, delta x, will delta y be positive or negative? Positive, positive. So what will the sign of the derivative be? Positive, right? So in a function of this kind, where you have the function, in locations where the function is increasing, the sign of the derivative is going to be positive. Where the function is decreasing, what's the derivative going to be? Negative. And right at the top, if the function is continuous and smooth as it's flattening out, the derivative becomes 0. And so also at minima, right? And now, when I'm speaking of multivariate functions, what do I mean by a multivariate function? A function which I'm speaking of a scalar function of vector variables. This board has a habit of sliding back up as I'm writing, so you have to watch out. Anyway, so something of this kind. You have x1, x2 as the argument, so it's a multivariate function. But the function value itself is a scalar, maybe a bold, right? Something of this kind. In this case, suppose I wanted the derivative at some point, and now x can be anywhere, right? How would you define the derivative? Yijing. Pardon me, can you speak up? Partial derivatives. Again, somebody else. So, Raymond.
Is it like you figure out the direction of the equal yield of the equation?
So again, going back to basic definitions, right? Yes, Maxwell. It's a vector, but exactly what kind of vector? Once again, the definition is exactly the same. A small step, delta x, in any direction is going to result in a change delta y, correct? And so now when I write it like this, I'm still going to write delta y equals derivative delta x. And this term alpha x is going to be the derivative over here, right? Is this a number? No. Now suppose, okay, I'll write this as transpose, okay. Suppose my input x is a column vector, then what is delta x? What is delta x? A small step. What's it going to be? A delta x is going to be a row vector? Column vector, right? So an increment in delta x is also going to be of the same kind, right? Because x plus delta x is a perfectly valid thing. So this result, is this result a scalar or a vector? So what must alpha x be? Alpha x is a row vector, right? And so the derivative in this case is going to be alpha 1, alpha 2, and so on. And the actual function that you're going to get is this term here. Delta y equals alpha 1 delta x1 plus alpha 2 delta x2 and so on, right? That's where the definition comes from, literally from the definition. Now, there are a couple of different ways to think about this. This is going to be useful. This is what I will call an before that, okay. Now, this step can be taken in any direction at all, correct? And the relationship must still hold by definition. I can choose to take the step along the axis, and when I take the step along the axis, then if I take the step along x1, for instance, this is going to be non-zero, but this is going to be 0. So your step is going to be delta x1 0, right? In that case, what is delta y? When only delta x1 is non-zero, what is delta y? It's just going to be alpha 1 delta x, right? Delta x1, correct? So in this case, when you're taking a step in only one direction, the result is the scaling factor is only alpha 1. This is now a function of can be defined in terms of two scalars. And so this is what is your partial derivative of y with respect to x1, right? And so your delta y is going to be the sum of partial derivatives times the increment in x. This clear to everybody? You guys at the back? Right, okay. And so now this again is a function of x. So the way I will represent it is using this inverted triangle form of representation, nabla x y, which says that it's a derivative of y with respect to x computed at some value, location. And this derivative is going to be a row vector of this kind, right? Now, there's another figure that I want you guys to think about. If I have a function which is a scalar function of many variables, right? Then this is what I will call a dependency diagram. Y depends on x1, x2, x3, x4, and so on, correct? And so when I have this, any increment delta y that results from increments delta x1, delta x2 is going to be delta x1 times alpha 1, which is the weight along this edge, plus delta x2 times alpha 2, plus delta x3 times alpha 3, times delta x4 times alpha 4. So we're going to use this diagram to show the dependency between variables. The weight on the edge, what is that? Alpha 1? The partial derivative, right? And so that's what we will use. Now, so I can rewrite things like this. Instead of using deltas, I'm using d over here. Now observe that this term, where's the rope? Okay, so we've written delta y equals delta x, right? This is a column vector. This is a row vector, okay? So I can think of this, the transpose of this row vector is often called a gradient. the transpose of the derivative. And the transpose of the derivative has the same dimensionality as x itself. It has to have the same number of components, right? Now what about this term? This is a vector, and this is a vector. So the two form an inner product, right? This is literally the inner product of the gradient and delta x. Now when we speak of, so what exactly do you think this gradient means? You have this gradient. The gradient is a vector, right? Which is the I'm speaking of the gradient, which is the transpose of the derivative, but the derivative is a vector, right? So it points in some direction and has some magnitude. What is the indication? What is the implication of this vector? Viraj?
It is the direction of the steepest change.
It is the direction of the steepest change. Why is that so? There's a vector in a product, and this was supposed to be animated, but because of the technical difficulties today, you don't have the animation. But here's what happens. Let's say I have two vectors, u and v. Then u dot v is simply magnitude u, magnitude v cos theta, right? So if I have some u, I have some v, the inner product between the two is given by this formula. When is this largest, Alice? When theta is 0, right? So now going back to our derivative over here, suppose again, look at this guy. This is a property of the function at x. That cannot be changed, right? What I can change is the direction in which I walk. So if I keep the direction, the length of the step fixed, I can take steps in different directions, right? When is this inner product going to be maximum? Someone at the back, when is this inner product going to be maximum? So I need my Yash. So yes, when is this inner product going to be maximum? When the two are in the same direction, right? So in other words, the function, this delta y, is going to be maximum when delta x is in the same direction as your derivative, right? So the gradient is basically the direction in which you have to walk for the function to increase fastest. And the magnitude of the gradient is going to tell you how fast it increases. Walking exactly opposite the gradient is the direction in which the function decreases the fastest. Obviously, it's the opposite, right? And that's where you'd want to go. And at the minima and maxima, if the function is smooth, the derivative is 0, right? So there's another property of the gradient. If you slice a function at a height, then the edge that you get is going to be what's called a level set, and the gradient is always orthogonal to the level set. We won't go into that. There's another property of functions, multivariate functions you might have heard of, called the Hessian, which is the matrix of second derivatives. Again, I assume you're familiar. Yeah.
I have a question. So you said the gradient is the direction of fastest increase.
Yes.
Can it be decreased as well?
Look at this. Which step? So, what is the, if I take a step along the gradient, will this be decreasing or increasing? It's a square, right? Delta x, both terms will be identical. It's positive. It's always increase. The negative of the gradient is the direction of fastest decrease. Right? Exactly. Okay. There's a pole. What is the pole number? 277? All of these were on my slides for some reason. So this one is just 277. Tell me when to stop it. 278 also? Okay, 77 and 78. Right. There were 5 poles, so there should actually be. Tell me when it's done. Okay, guys, moving on. I think you know the answers to the questions, right, at this point. Here it is. At any location x. Now, there isn't just one direction in which you can walk to increase the function, as you can see, when you have a multivariate function, like in the bowl, right? There are many directions in which you can walk to increase the function. There's one direction in which the function increases fastest. So the gradient is the direction of the fastest increase, but there are other directions in which you can walk where the function will also increase, right? And the derivative of a scalar with respect to a column vector is a row vector. We just saw this, right? Now the function, for the problem of optimization, we are 40 minutes into the class and I haven't even begun. This is horrible. Okay. The problem of optimization. The problem of optimization is you're given a function of this kind. You want to find either a minimum or a maximum. Basically find the location. Like if you were asked to find a minimum, you'd be trying to find the position of the red arrow to the left. For the multivariate function, you'd be trying to again find the position where the bowl takes its lowest value, right? Now, do you remember how, given any odd function, you would try to minimize it, Benjamin?
Well, I mean, you can take the derivative and find where it...
You can take the derivative and find out where it goes to 0, right? So that's going to be something like this. Find the derivative. You know if the function is smooth and continuous, then it's going to keep decreasing, and then beyond the minimum, it's going to begin increasing. At the minimum, it's flat. So the derivative is 0. So if it is checking the derivative, whether the derivative is a 0 or not sufficient to find out if it's a minimum. There's another pole. Yeah? This one is 279. Done? This is an easy one, guys. So I'm only giving you 45 seconds. All right. So we're done, okay? You know the answer, but we'll go back to it, right? So is it sufficient to simply check if the derivative is 0? What else must we do? Shreya, what else must we do? The second derivative. Check if the the sign of the second derivative. What is the logic behind it? Here it is, right? So maxima and minima are what are called turning points. Why is it a turning point? When you're at a maximum, as you approach it from any side, the function keeps increasing until you hit the maximum, and then the function begins to decrease. So the function has turned, right? Similarly, at a minimum, regardless of where you arrive at it from, it's decreasing, and then you hit a minimum, and then it turns and it begins increasing. So both of them have 0 derivative, which means if you plot the derivative of the function, at a maximum, the derivative is going to be positive before the function because the function is increasing before the maximum. After the maximum, the function is decreasing, so the derivative is going to be negative, right? So if you plot the derivative, it's going to go from positive to negative. It's going to hit 0 at the maximum. Similarly, at a minimum, before the minimum, the function is decreasing, so the derivative is negative. Afterwards, it's increasing, it's positive. So the derivative is going to go from negative to positive as 0 at the minimum, right? If you take this second derivative, what happens? That's the derivative of the red line itself. That's going downwards at a maximum and upwards at a minimum, right? And so the second derivative is going to be negative at maxima and positive at minima, which is why our test is check the derivative, find out where it's 0. At that point, you check the second derivative. If it's positive, what is it? Is it a minimum or a maximum? It's a minimum. And if it's negative, it's a maximum, right? Easy test. So the maxima and minima are not the only places where the derivative can go to 0. So you can have a function like the one on top, and you see that the derivative is going to 0 at 3 places. Where? Bill? the max, then there's a point in the middle where it flattens out, and then again at the minimum, right? So the plot over here, observe what is happening with this, with the derivative. At the maximum, the derivative is going from positive to negative. At the inflection point, the function is decreasing, then pauses for a while, then continues to decrease. So the slope goes from negative, but hits 0, then goes back to being negative, right? And again, at the minimum, it goes the other way. Now, if my function were like this, what would the derivative look like? What would the shape of the derivative be? Xiaoyang. It's going to be like a bowl, right? It's positive. The derivative is going to be positive initially, and then goes to 0 here. This is 0, and then goes back to being positive. Regardless, at this point, the second derivative, what is the second derivative going to be? What will the second derivative be at the inflection, Saida? 0, right? It's where the derivative is flat. Correct? And so when you actually plot these second derivatives, they're going to look like so. They are going to be negative at maxima, positive at minima, and you can't really say what it's going to be like at the inflection point. It's going to be 0, right? So now that's for functions of a scalar variable, but similar properties hold for multivariate functions. For a multivariate function too, a minimum is a turning point. You begin walking in some direction, you hit a flat region, then you begin walking in the other direction, right? So the function turns. Both minima and maxima are turning points, and if the function is continuous and smooth, at these minima and maxima, the derivative will be 0. So if I'm trying to find where the function is minimum, I'm just going to compute the gradient of the function and equate it to 0, right? So here's how the unconstrained optimization problem is going to look like. You can compute the gradient, equate it to 0. You don't know if it's a negative or if it's positive, if it's a minimum or a maximum. You compute the Hessian, and the Hessian is, and you'll have to check if the eigenvalues of the Hessian are all positive or negative. Anyway, we won't spend too much time on it right now. There's a little example that's supposed to be a hidden slide. But here is the problem. This kind of optimization is not going to be possible in the general case. You cannot simply write the function. I mean, for example, if I have some cute little function of this kind over here, then I can actually write the formula for the derivative, for the gradient, equate it to 0 and solve, right? Something like this. That function doesn't have the kind of form where I can compute the derivative, equate it to 0, and just get the answer. So in this case, I'm going to need iterative solutions. I'm going to start with a guess and then keep updating my guess to get to the right answer. So you would have a solution of this kind. I have both the one-dimensional and two-dimensional bivariate illustrations. You start with some initial guess and say, this is where I think my minimum is. Then you check, and you say, nope, this is not the minimum, so I'm going to move. And then you go to a place where hopefully the function is smaller. And then check again, and then if that's still not a minimum, you take another step and keep repeating this till you arrive at a minimum. So the question is, I know that if I can find out that the current place is not a minimum, which direction do I walk in, and how big should the step be, right? And so these are the two main problems with this iterative approach. But let's answer the first question, which direction should I walk in? To answer for that, let's consider here this. If I have a function of this kind, right? And if I'm currently over here, if I look at what will the slope be over there at that location? Is it positive or negative? Why? Because a small increase in x increases y, right? So which way should I move x, forward or back? Backwards. Suppose the function is like so, and I'm over here. What will the slope be like? Negative. Which way should I move x? Forward. So that's the size. Whenever there's negative, you have a negative derivative, you're going to, if I'm trying to minimize my error function, right? If the derivative is negative, it means I have to go forward to continue decreasing it. If it's positive, I have to go backwards to decrease it. And so you have this you end up with this rule as a consequence. You check at each position. If the derivative is 0, it's flat. You're likely at a minimum. If it's not 0, you check the sign. And if the derivative is positive, you take a step back. If the derivative is negative, you take a step forward, right? So if the derivative step has to be positive in every case, right? So it's minus step or plus step. So I take a step back or I take a step positive. I can write that in one simple formula. I can just say steps are minus step times the sign of the derivative. Why is that? Because if the derivative is positive, this is going to give you a negative step. If the derivative is negative, this is going to give you a positive step, right? So it's an easy, this is identical to what we just had. But then instead of just looking at the sign of the derivative, I can do something even smarter. I can take the entire derivative itself. So this naturally captures the sign. I'm going to take a step against the derivative if at every point, okay, if I'm trying to minimize the function. When I'm taking, so what this means is if the derivative is positive, I'm going to go back. If the derivative is negative, I'm going to go forward. But then I'm not just using the sign, I'm using the entire value of the derivative. So Alice, answer this question. Can you wake her up? You. So suppose I have a function of this kind, and my current estimate is over here. Is the magnitude of the derivative going to be large or small? Larger, okay? Am I close to the minimum or far away from it? I'm relatively far away, right? So do you want to take a bigger step or a smaller step? You want to take a bigger step out here, right? From here, you want to take a bigger step. Out here is the derivative, Alice, you again, is it going to be small or large? Do you want to take a small step or a big step? You want to get more careful as you approach the minimum, right? So that gives you this natural property. When I use the derivative itself, it gives you this natural property that it's sort of, it's very useful for bowl-shaped functions. When you're very far away, it takes big steps. When you're close by, it takes smaller steps, right? So there's a point. 298, guys, this one. 98? Huh. Okay, time? We'll stop at 45 seconds. We lost some time today. Time's up, right? So select all that are true about derivatives of a scalar function of multivariate inputs. At any location x, there are many directions in which we can step, such that f of x increases. The direction of the gradient is the one where the function increases fastest, right? Those are the only true facts. Okay. So here we are again. The gradient is going to be 0 at the minima or the maxima, right? And at any point, if you're going to go towards the minimum, you know that if you walk in the direction of the gradient, the function increases fastest. If you walk exactly opposite the direction of the gradient, the function decreases fastest. This is even for multivariate functions, right? And so that gives us back the same rule. If I have an iterative estimate, then at the kth estimate, if I want to decrease the function, I'm going to take a step against the derivative, right? Now, there's still this question of how big the step must be. So that's a step size term over there, eta, and we'll deal with that later in a couple of lectures. But the point is you take a step against the derivative, proportional to the derivative if you want to go to a minimum. You want to take a step in the direction of the derivative, again, proportional to the derivative if you want to go towards a maximum, right? So this gives us the gradient descent algorithm, which is this guy again. You initialize your x, and then at each estimate, you compute the derivative at the current location, and then take a step against the derivative. That's your gradient descent. You're always walking against the gradient to arrive at the minimum, which is why it is the gradient descent. Then when do you stop? You can keep continuing to take steps. At some point you have to stop, right? You can try to compute the derivative at the current location to figure out whether to stop or not. But it may not always be feasible to compute the derivative. It may be easier to just compute the function value, which is part of your computation. So if you find that if the function hasn't changed between the previous step and the current step, just stop, right? So it's going to be feasible to compute the derivative, but you may not. They're just alternate criteria. All right. So this is your gradient descent algorithm. You initialize x0, and at each time you take a step against the derivative until either the length of the derivative is too small or how much the function has changed by is too little. Yes?
Are we assuming the derivative is also like smooth everywhere?
I'm speaking of smooth and continuous function, continuous and differentiable functions at this point.
Okay, so the derivatives are also smooth.
Pardon me?
So the derivatives are also smooth.
The derivatives exist is all we are saying. We are not speaking of the second derivative, so there's no need for the derivative to be smooth.
So like, it is not smooth when our assumption about like, if its magnitude is large, then we like are further apart from where it's 0 because it's.
So the function, it's the gradient descent rules mechanism is sort of designed for those such functions, but you use it anywhere pretty much. That's where the step size becomes an issue, right? If it's a nice bowl-shaped function, pretty much most step sizes will get you to the minimum. For other functions, you've got to worry about how big a step to take. We'll deal with these later, right? So now, actually answering your question in part, if you have functions of this kind, for a bowl-shaped function of the one on top, the gradient descent rule is kind of guaranteed to get you to the minimum in a reasonable amount of time. If you have uglier functions, there's no guarantee that you will actually get to a minimum. You can get to an inflection point. You can get to a local minimum, which is not the global minimum. You can get stuck in other places. We'll deal with these later, right? So what is the pole number here? 280. We are bouncing back and forth, but this is 280. Stop it at 45 seconds. Done? We are done, guys. Okay. The answer is, of course, on the slides, right? So now, what we were doing so far was we were taking a detour from the basic problem that we started off with, which is that of trying to train a neural network. We defined a loss function, which is the average divergence between the training and between the desired and actual outputs of the network. This is a function of just the weights of the network, and we are trying to minimize this function with respect to the weights. And so naturally, typically it happens that these loss functions are not these nice, beautiful functions where you can write the derivatives and equate them to 0. So because they are complex, we are going to use gradient descent. You initialize all of your parameters. At each point, you compute the current derivative if it's not 0. Then you take a step against the derivative. You modify all of the parameters against the derivative and keep repeating this process till the loss sort of no longer changes, right? So now, before we do that, we need to define various things about the problem. So you at the back, is that a Saturday Night Live t-shirt? No. Right there, you. I can't read your name tag, yes. You have to write fatter. To me, it looks white. I'm blind. Okay. So what are all the things I'm missing over here for me to solve this function? What are the things I must define properly? Remember, I'm trying to train a neural network on real life data. What are the things I must define? Pardon me? The divergence function. What else? The activation. No, that's F. What else? I have to define everything, right? What are these input-output pairs? Right? You start from scratch. You're taking a lot of things for granted. What is this function f that I'm trying to, compute the output of and, and optimize? What is this divergence function? Every one of these things has to be defined. Otherwise, I don't have a mathematical problem to solve. And so let's start off with looking at this. We're going to generally assume that this f is our multi-layer perceptron, where we will generally assume a directed network. And we defined a directed network in the last class. So Abhi, how did we define a directed network?
I'm sorry, I can't recall.
Okay, Eric?
We were just saying that with your sources and sinks, we're always moving through parameters.
Sahitya, how did we define it?
So it propagates forward to the network and then leaves the loss and then
So what did we mean by saying it propagates forward? Yes.
The path taken only moves forward in the number of layers.
And each layer operates only on the outputs of the previous layers, right? So this was and there are no loops, therefore. The information never goes back and revisits any node. So this was our directed network. We're going to assume a layered network, which is meaning that there is a source and a sink. Now, if I have a directed network with a loop, then what is the layer number for any node on the loop? It's infinite. I can just keep going around, right? So if you have a layered network, loopy network, the definition of a layer kind of falls on its face, right? So we're going to consider a loopy network, sources and sinks, as Bharat just mentioned. Each layer only gets its inputs from the previous layers, and there's a final output layer from which we're going to read the outputs, and everything in between is going to be called a hidden layer. And each layer in between, the layer consists of elements which are very simple. This was the basic idea that we began with several classes ago, right? And our basic unit is going to be a neuron, a perceptron, which has a two-step operation. In the first step, it computes an affine function of its inputs. In the second step, it applies a activation to this affine function. And we want this this activation function to be continuous. We would like it to be differentiable. Sometimes they won't be, and we'll see how we deal with those as well, right? And so that's how we define our basic unit. But in general, it doesn't have to follow the format up there. You can have other kinds of formats. You can have any differentiable function of its inputs as this neuron. But we're going to assume the two-step function, where first you have an affine function being computed of the inputs, and then an activation is being applied to it. And so here are various kinds of activation functions. The first one is the sigmoid. It's 1 over 1 plus e raised to minus z. It goes from 0 at minus infinity to 1 at plus infinity, and then it smoothly curves between the two. Now you can see why this happens, right? So the sigmoid looks like so. I have 1 over 1 plus e raised to minus z. If z is minus infinity, then what is minus z? Positive infinity. What is e raised to minus z? No, z is minus infinity. So what is e raised to minus z? Positive infinity again, right? So 1 over positive infinity is going to be 0. So out here on the left-hand side, far away, it's going to be 0. If z is plus infinity, Soumya, what is e raised to minus z? Z is plus infinity. What is e raised to minus z? It's e raised to minus z, exponent of minus z. What will it be? That's going to be 1 over e raised to z, right? So what will that be? That'll be 0, right? So when z is plus infinity, this term is going to be 0, this guy. So 1 over 1 plus e raised to minus z is going to be 1 out here. And so and it sort of smoothly goes between the one and the other. And what is the derivative of the function of this function? The derivative of this function is clearly going to be, add some colored chalks. That is up here, there. So the derivative of this function is clearly going to be 0 out here. It's going to be 0 out here as well because it's flattened out. And then it's going to be something of this kind where the peak value is half. Then the other activation people like is the tan H, which is basically the stretched and shifted sigmoid. And that also has the same shape, except it goes from -1 to 1. And the derivative peak is actually going to be 1, not half. And then you have these other activation functions, the ReLU, which is 0 for all negative inputs, 1 for and equal to the input for all positive output inputs. So what is the derivative of this one going to be? Wrong? Yeah? What's the derivative of the ReLU going to be? Wrong? Yeah. So the ReLU looks like this. Stop falling. So guys, wake up. I shouldn't be more awake than you. The ReLU looks like this. What is the derivative of this going to be, one? Pardon me? And? So the derivative is going to be like that, correct? And so then the soft plus is a smooth version of this guy, which looks like this. The soft plus looks like this, and the derivative of the soft plus is actually a smooth version of this one. It's a sigmoid. Okay? So these are the different kinds of, and there are several other activation functions that we use. There's also something that we will call vector activations. I can think of a vector activation which takes an activation which takes a bunch of inputs and produces a set of outputs, right? So you can't think here of individual inputs and individual outputs. You say that it takes this entire collection of inputs and produces this collection of outputs. And the most popular one is the Softmax. All of you have encountered this or will be encountering it very, very shortly. Now, it takes a bunch of inputs, say k inputs, but it does the computation in 2 steps. First, say it's producing L outputs. It is going to compute L independent affine functions of the input. And then, after computing L independent affine functions of the input, it exponentiates each of these affine values, but then normalizes them to sum to 1. Okay. Now, there's a critical difference between an activation function of this kind, which has many outputs, right? And something like, if I thought of the second layer over here, the second layer is also effectively a vector activation. It takes a bunch of inputs and produces a bunch of outputs, right? But what is the key difference between something over like this and the Softmax? Yipen, can you tell me? Yes, Viraj.
The softmax will always have a value between 0 and 1.
No, but there's something more in terms of derivatives, right? Yeah.
Softmax uses information from adjacent nodes.
You get information from adjacent nodes. So look at this guy. In this one, if I perturb one of the weights, how many outputs will change? In one of the intermediate layers, how many outputs will change if I perturb one of the weights? Exactly 1, because the only thing that it's being connected to, right? Whereas if I go out here and perturb one of the weights, what happens? The corresponding affine function changes. The rest of them don't change, but because of the downstream normalization, everything changes. So if I change the weight such that one affine value goes up, the corresponding softmax output goes up, but the rest of them go down, right? So that's why I'm calling it's different in the sense that perturbing one parameter can change all the outputs. So in a typical network, you can view all of the layers as vector activations, but something like the softmax is different in that changing one parameter can change all the outputs, right? Now, so we've defined the function f. Now let's look at how would we define the inputs and the outputs. Now when I'm speaking of defining the inputs and outputs, there are three things I must define. I must define the inputs themselves, then I must define the desired output, and I must define the actual output that the network produces. So if you for each input output pair, observe that there are three terms over here. There's the x, I have to specify x. There's the d, I have to specify d, and there's the y, which is the network, what the network actually produces, and that too must be specified, and they can all be very different, right? So if I have a vector input, if my inputs are vectors, then my input is going to be some d-dimensional. Every input vector is going to be some d-dimensional vector. If I have many outputs, then the desired output is going to be some l-dimensional vector. The actual output is also going to be an l-dimensional vector, because in the best case, the actual and desired outputs are the same, right? Now, I'm going to be speaking only of a single input. In reality, you'll be dealing with bunches of these guys, but to specify these, it's enough to consider one input. Now, representing an input is, yes, Viraj?
So if we consider the first hidden layer and it is y1, y2 up to yn, do all the neurons of the second layer receive all the inputs? Or
Depends. That's the same. Effectively, yes. It's, even if they don't, that's like having zero weight, right? So now, this is a network. It works on a computer. It doesn't work on magical objects like pictures and and chessboards. It works on numbers. So the input must be represented as numbers, and therefore your input is always going to be a vector of numbers, or even just a scalar if you're working on scalar inputs. So if you're working on images, the input is going to be a vector of pixel values, which are actual numbers. If you're working on speech, the input is going to be a set of real numbers, which are features computed from the speech. If you're working on text, as a first step, you're going to have to convert the text into a collection of numbers, and that's what the input is going to be working on, right? So, or it could just be, if you're working on some kind of a regression problem, it could be just a collection of real numbers. So defining the input is very easy. Representing the output is slightly trickier. Now, I can have, if I'm just performing a regression task where I'm computing real valued outputs, then it's easy. The output is the number that you want to compute. So the desired output is going to be a real valued number, right? And your network is also going to have just one output. Or if you're trying to predict vectors, real valued vectors, then the desired output is going to be a vector of numbers, and the network is going to have as many outputs as you have desired outputs. So that works. If you're performing something else, if you're performing a binary task, like the output must be 0 or 1, like in classification, is this a cat or is this not a cat, right? In that case, it's a binary task. You're going to convert this output to a binary value. So if I'm doing a two-way classification task, I'm going to say the presence of the class is 1, the absence of the class is 0, or the presence of the class is 1, the absence of the class is -1. It doesn't matter, you're converting it to two numbers. So, and in this case, your network is going to typically have just one output, which ideally produces either the one value or the other value, right? So now, that is the desired output. What is the actual output of the network? The actual output of the network is going to be a sigmoid. We saw that the network will actually have sigmoid activations, right? And what is the difference? So in the binary case, the desired output is going to be either a 0 or a 1. The actual output is going to be some value between 0 and 1 computed from a sigmoid, which you can view as the probability of the output of the target class. So you can say this is the probability that the output value is, that the class is 1. So, this has to do with the fact that in real data, in the real world, you can never be 100% certain 100% of the time, right? So you actually end up computing probabilities. Very simple. Now, if I have a multi-class output, so I'm still performing a classification task. I have to distinguish between dog, cat, camel, horse, whatever, several classes of flower. Then this is a bunch of labels, dogs and cats are not numbers. So we have to convert this to some numeric representation. So the first thing that we will do is to order our classes in some prearranged order, like say alphabetical, dog, cat followed by dog followed by camel. That's not alphabetical, some order. Cat, dog, camel, flower, right? Hat. So now if you have n classes, this ordered list is going to have n entries, right? Then you're going to define your desired output as an n component vector, one per entry. And the arrangement has already been specified, right? And now if you have, let's say, if the three classes are say cat, dog, elephant, then if I get a training instance which is an instance of a cat, then the desired output is going to be 1 over here, 0 and 0. If I have a training instance which is a dog, then this is going to be 0 over here, 1 over here, and 0 over here, right? And if I have a training instance which is an elephant, that's going to be 0, 0, and 1, right? So you get the idea, right? This is a numeric representation of your target class with a 1 in the correct position and 0 elsewhere based on the order. It's called a one-hot vector because only one of the entries is 1, all the rest of them are 0. So we will use one-hot vectors for representing the desired output of the network. What about the actual output of the network? That's going to be more challenging. So I've got to check the slide numbers. Okay. For a multi-class classifier with n classes, I need n outputs, right? But now in the case of the multi-class classifier, the outputs are going to be probabilities. They are not going to be binary numbers because, as we know, the network can never really be sure. So what we want the network to produce is, for a cat, now think about this. We can think of these as probabilities. When I give you a training instance and say this is a cat, then the probability that it's a cat is 1, that it's not one of the other classes is 0, right? So the idea, I want the network also to produce P1, P2, and P3, where this guy is high and these two are low. So in the case of a multi-class classifier, the actual output network is going to be a vector of probabilities. In the ideal case, they're going to be all 1s and 0s, 1 for the correct class and 0 for the other classes. In reality, it's going to be a bunch of other non-negative numbers that sum to 1. And so what kind of activation actually gives you a collection of numbers which are all positive and sum to 1? That's the softmax. And so when you have a multi-class classification problem, you actually have the output layer be a softmax layer, which computes the kind of probabilities and which has the capacity in the limit to actually compute a probability pretty close to what you want. But in reality, it will give you something else most of the time, right? And so in the multi-class classification problem, the output of the network is going to be computed by a softmax layer typically, with as many outputs as classes, and it will output probabilities. So now that we've defined inputs and outputs, we can sort of specify how a problem might be presented for learning. You'd be given a collection of training data instances like images of digits, along with information about which digit the information represents. And then you could have tasks like binary recognition. Is this the digit 2 or is it not? Or you can have multi-class recognition. Which digit is this, right? And if you're given the binary task, then your training instances are going to be images of digits, which we will convert to vectors of pixel values. Along with each, you'll have a binary label, a 0 or a 1, telling you whether the number is actually a 2 or whether it's not a 2. And the network is going to have only one output, right? If you want a multi-class classification, you want to specify which digit it is. So along with each instance, now you actually give the true label, but you're going to give it in implicitly in the one hot form, right? And the network itself is going to have as many outputs as the number of classes. And given this information, we must train the weights and the biases of the network. So we've defined the function f and the inputs and the outputs. But there's this one last thing that must be defined. And this is key. If we don't do this right, then you're not going to get the network to work. And so remember, we want the loss to be differentiable, right? For the loss to be differentiable, the loss is a function of, loss depends on this divergence function. The loss depends on the function f, which is the network, which in turn depends on the activation functions inside the network. So for the loss to be differentiable, all of these have to be differentiable, right? Which means you need a differentiable divergence function. Differentiability is not a standard property of divergence functions. It's not required. But in our case, we want it to be differentiable because otherwise we will not be able to compute the derivatives required for gradient descent. So it's very important for the divergence function to be differentiable. Now you have different kinds of problems. I have 10 minutes. I'll try to get through this in 10. If you have a regression problem where you're trying to predict real numbers, then there's a very, very nice loss function that we can use, which is the L2 divergence. It's very popular. And the L2 divergence is defined simply as half of the squared Euclidean distance between the actual output of the network and the true output of the network. This is useful when you are trying to make real valued predictions, right? Now, why do we need the half? Remember that I want to compute derivatives, right? So the first thing I want to do when I'm computing derivatives is to compute the derivative of the divergence with respect to the output of the network. So if you take the derivative of this L2 divergence with respect to the output of the network, what are you going to end up with? You're just going to get y minus d, right? Because the 2 factors out the half on the outside. That's why we have the half. And so now this is very beautiful. The derivative is simply the error, right? And so this is why when people first worked on back propagation, they called it error back propagation. If you use the L2 divergence, the derivative of the L2 divergence defined with the half is just the error. And so that is what you would be sending backwards through the network. Now, for binary classification, things get a little more interesting. For binary classification, you can think of the output of the network is either a 0 if it doesn't belong to the class, or a 1 if it belongs to the class. This is the desired output of the network, right? You can think of it as the probability of the class. If the input doesn't belong to the class, the probability that it belongs to the class is 0. If it belongs to the class, if you're certain that it belongs to the class, then the probability of the class is 1, right? So this is the desired output of the network. And the output of the network, the true output of the network is going to be some number between 0 and 1, which is going to be the probability of the target class. So there's a corresponding 1 minus p, which is the probability that it does not belong to the target class. And so now you have two probability distribution functions. You can define the so-called Callback Liblar divergence between the two, okay? And the Callback Liblar divergence between the two is going to be defined as, let me call this d and 1 minus d, right? So observe that if it belongs to the target class, d is 1 and 1 minus d is 0, right? If it doesn't belong to the target class, d is 0, 1 minus d is 1, right? And the Callback Liblar divergence is going to be defined as minus of d log p times 1 plus minus 1 minus d log 1 minus, I call these y, right? Okay. Now observe what happens over here. If the target output is of the desired class, then d is 1, right? 1 minus d becomes 0. So this simply because when the target output is of the desired, when the input is in the target class, D equals 1, implies that divergence is simply going to be, what is it going to be? Anyone at the back want to tell me? One of you, the lady over there who's writing, yeah. Hello, you there? So when the target class is 1, what is the divergence going to be? Can you speak up, please? Yes. Alex, can you tell me? So this is how I've defined my Callback Liblar divergence. I know all of you are asleep, so am I. Wake up, okay? So that's how you define your Callback Liblar divergence. When I give you an input that belongs to the target class, what is the value going to be? What is D when the input is to the belongs to the target class? 1. So what will it be? This is just going to be minus log y, right? Because the second term 1 minus D becomes 0 and D is 1. When the input doesn't belong to the target class, what does this become? Anyone at the back want to tell me? It's going to be minus log 1 minus y, right? And now, if the actual output of the network is correct, and so if D equals 1 and y also equals 1, what will the divergence be? If D is 0 and y is also equal to 0, because you get log of 1, right? If D is 1 and y equals 0, so the desired output is 1, and it gave me it told me that it was 100% sure that it was not in the target class. Then what would the divergence be? What would it be? What is log of 0? Minus infinity. So minus and minus is going to be plus infinity, right? And so also the other way, right? So now, we've looked at L2 divergence. Why can I not use the L2 divergence when I'm performing binary classification? Here's a reason why, right? The red curve gives you the L2 divergence between the output of the network and the desired output of the network and the binary classification curves. A problem. It's a nice smooth curve, right? It's like a bowl. But then it's missing something important. If it's a cat, and if the network says I'm 100% sure it's not a cat, is it just slightly wrong or is it infinitely wrong? It's infinitely wrong, right? The Callback Liblar divergence captures this fact. So if you look at the KL plot, it shoots up to infinity, right? So also, if it's not a cat and the network says I'm 100% sure this is a cat, is it infinitely right or wrong? It's just not slightly wrong, it's infinitely wrong, right? So once again, the function has this property that it shoots up, okay? Both of these divergences have the value 0 when the target and when the desired and actual outputs are identical. But there's something interesting over here. What is the derivative of the L2 divergence, the bowl, when y equals D? In both cases, it's 0, right? Because, when the desired class is 0 and y is 0, the red curve becomes 0 and then increases, right? So also when the desired class is 1 and y is 1, that is the figure to the right, it becomes 0. In the KL divergence, if the desired output is 1 and the network output is also 1, what is the derivative? What is it? It's negative 1, right? So also when the desired output is 0 and the network is correct, what is the slope? That's the figure to the left. What is the slope of the blue curve, which is the KL divergence, when the network is correct? Someone at the back, all of you are sleeping. Okay, can everybody say this aloud together? Just say 1 along. Come on, 1, 2, 3, go. Say it. 1. Say it again, it's not loud enough. 1. Thank you. And so in the case to the right, when the desired output is 1 and the network is right, what is the slope of the loss? Together, everyone, I need you to wake up. Come on. Thank you, right? So does this mean that the derivative is always going to be 0 at a minimum? No, right? So what we've seen in this interesting function is that I'm giving you this function which has the right properties, but unfortunately the derivative is not really going to be 0 when the output of the function is right. So now when we were looking at the gradient descent rule, I gave you the objective I gave you to decide whether to terminate or not was whether the function was decreasing with the iterations, and I was not actually checking the derivative. Why? Does this tell you? Varshita, can you tell me? Can I use a gradient descent rule and say I will continue running my iterations till the derivative becomes 0? No. Why not? It is not 0 in this case, right? So checking for the derivative is not the best thing you can do. You want to check if the function's actually slowing down to nothing, right? So now here is the actual function for the derivative. It's minus 1 over y when the desired output is 1, and it's minus 1 over 1 minus y when the desired output is minus 1. Now observe something interesting, right? Again, at all points, if the desired output is 1, if the derivative is minus 1 over y, what will gradient descent be encouraging? Will it be asking you to increase y or decrease y? Y is always positive, correct? So 1 over y is going to be positive, correct? So what is the sign of the derivative? Negative, right? So if the derivative is negative, what does gradient descent ask you to do? It asks you to increase y. So when d is 1, it's always going to ask you to increase y, right? When the desired output is 0, what is it going to ask you to do? You want 1 over 1 minus y. The sign is always positive, right? If the sign of the derivative is positive, what is it asking you to do? It's asking you to decrease y, right? Which makes sense, right? It's very intuitive. Now, I'm going to go over by a few minutes to make up for tech difficulties. Please spare me the time, right? Last topic. When we speak of multi-class classification, we actually have a one-hot output, a desired output, and the target output, which is a probability distribution. So I have two vectors, both are probability distributions, and I can once again define a Callback-Liblar divergence between the two. And so the Callback-Liblar divergence between two probability distributions is defined as, the formula is right up there, summation, this is the desired output, log of di over yi, which is going to be summation I di log di minus summation I di log yi. Okay. Now, at any component, the desired output is either 1 or 0, correct? When the desired output is 0, what does di log di become? 0, right? When the desired output is 1, what does it become? It becomes 0 also, correct? So the only term that remains is this guy to the left, to the right, which is minus summation di log yi, okay? And this is what is also called the cross entropy. So when you're working with your neural networks, you will often encounter the term cross entropy loss rather than the Callback-Liblar divergence. They end up being the same thing when you have one-hot representations, right? And now, what is the derivative of this cross entropy loss? How many of these di's are going to be? Can I simplify this further? What is it? Because all of these di's are 0. There's only one di that remains, right? So that is simply going to be minus log of whatever output was given to the correct class. Okay? And once again, so when I take the derivative of with respect to of this with respect to the outputs for the various classes. The loss is a function of only the probability for the correct class, correct? And so the derivative is going to look like so. It's 0 everywhere, and it's going to be minus 1 over the probability of the correct class for the correct class. Now tell me this again. If if I were to use this formula for this derivative in gradient descent, what does it encourage me to do to the probability of the correct class? Because minus 1 over y is always, is it negative or positive? Negative. So it tries to increase y, right? So when you plug this formula into gradient descent, it's always going to try to increase the probability of the correct class, which also makes sense, right? And once again, when the output of the network is exactly right, the derivative is not 0 for the same reason that you saw here, right? So earlier, so you've got to be careful about that. Now, so all terms have been defined. There is a fifth pole that I will skip because we're out of time. And so here's the story so far. We've rushed through the class. You'll have to bear with me. And guys, I brought myself coffee. I'll pay for your coffee. Bring it. Wake up. Be awake. Okay? And if I find any of you sleeping in class, I'll come over to your position. I'll wake you up. I'll send you out and have you buy coffee. That's very embarrassing. Don't do it. Okay. So here's what we've got. Neural networks are universal approximators. We've seen that they are trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual and desired outputs. And to train these, several terms have to be defined. The network itself, the manner in which the input is encoded as numbers, the manner in which the output is encoded as numbers, and the divergence function that computes the error between the actual and desired outputs, for which we typically use the L2 divergence for real valued predictions and the Callback Liblar divergence for classification. So we'll stop right here. If you have any questions, please post these on Piazza. Thank you.